Okay, Joel gave me a title, which I will try to speak to, which is Expand Topical Areas Covered by UC-HiPACC. And I'm actually going to just talk about one, which has already been introduced today by Saul Perlmutter, and that's data science. Okay. And I'm going to introduce it this way. We've had Exascale mentioned a number of times today. The people who are in DOE labs just assume that it's going to happen. The people who are not in DOE labs hope it's going to happen. But I'm here to tell you that Exascale, the initiative, has been hijacked by big data. This is a website for the first Big Data and Extreme Scale Computing Workshop, which was run last year somewhere in Europe. They just had the second one in Japan a month ago, and these things are organized by, the power elite of the DOE, both the science side and the national security side. And why are they doing this? Well, I got my hands on this document, which is not in wide distribution. This is the DOE Exascale strategy. It was delivered to Congress June 2013. It was a year late, and the death of Mike Strayer complicated things and delayed things. But the reason why it was a year late is everyone is scrambling on account of two things. One is no one knows what the technology is going to be to build an exaflop HPC system. And number two, the big data phenomenon happened. So staffers in Congress on appropriations committees said, why should we put $1 billion into simulating something at an exaflop when big data seems to be the new thing? So an interesting thing happened between edits of this document. Essentially, if you read this document, which I have, basically they did a pattern replace of high-performance computing with high-performance computing and large-scale data analysis. And if you read down some of the highlighted text, large data problems, this paragraph here, relationship between exascale and large data. As currently planned, DOE exascale computers will be designed to process the very large data sets derived from anticipated computational, experimental, and observational sources. So politically, extreme scale computing and big data computing have been merged. And so now this community that just a couple of years ago hoped to get $1 billion to build an exaflop computer, now are hoping they'll get $1 billion to build an exaflop computer that can also do exascale data analysis. So that is an indication that the landscape of high-end computing, high-end scientific computing is changing. And it's trending. Okay, so what's that? But it gave rise to an academic discipline, which we call computational science. In the same way, big data is giving rise to an academic discipline that we can call data science. In the late 80s and early 90s, computational science and engineering programs sprung up across the United States. Hundreds of programs were created. And now data science programs are starting to spring up, but it's in its very, very early days. And the program that Saul told us about earlier today is one of the first and perhaps the most high-profile one that I know about, but it is just starting. So let me make a few observations. And others have already alluded to this, that now supercomputers are just another data source, and they're producing large amounts of data, especially in areas like cosmology. And the difficulty is in the data analysis and data management. Now, many of us, we look at our experimental colleagues who work in large projects where the data management, data analysis is actually built into the planning and the budgeting and the operations and so forth. And I can see a future where operationally, computational science just becomes kind of a subset of science, which has perhaps a computational stage in the front end, but the hard part, the 90% in Matt's diagram, is the data analysis, the data management. So at the end of the day, data science and computational science are just going to merge into one thing. It's going to be computer-based science. And it's going to have some simulation, and it's going to have some analysis, and there's going to be lots of data to manage. So if you think about the agencies that have lots of experience in doing big data science, if you will, it's NASA, DOE, and the NSF is just starting to figure out what it wants to do in that space. But I think if you look at where all the sort of free energy is coming in the NSF world, it's in big data programs or computational data and science, computational and data-enabled science and engineering. So these are signs that this is what is happening. Now, HiPACC is, I think it's got an intelligent name. It's astrocomputing, but it in principle spans both sides, right? But I think my view is it's very simulation heavy. And so my recommendation is in the next incarnation that it embrace data science. And what a great place to be doing that here in California when you consider not just what's going to happen here at Berkeley, but what is going on at NERSC, at San Diego, at Livermore, Los Alamos. We're really in an ideal place. Now, data science is this incredibly multidisciplinary thing. It's, you look at these things that look like cometary orbits, you know, if we just start at the top, it involves statistics, pattern recognition, neurocomputing is making a charge, AI, machine learning, operations research, data mining, databases and data processing, visualization. And the thing that's in the middle is data science. Now, in the same way, you could draw a diagram like this for computational science, where you'd have things like numerical algorithms, and you'd have things like computer architectures, parallel programming languages, compilers, all that stuff. And those sit in various academic departments. But to do computational science at the high end, you need the union of all of that. So data science is really a similar sort of thing that is equally multidisciplinary. The job problems exist in both areas, but computational science has actually matured quite a bit relative to this. So we're really on the ground floor of a new kind of science, that a new methodology that will just complement the other three, and at the end of the day, it'll all be part of how we do science. Now, if you think about computational astronomers, of all kinds of scientists, computational astronomers do a lot of this already, often without a formal education, or awareness of algorithms and tools. And as we heard from Saul, BIDS at Berkeley is going to address this gap. So a lot of it is sort of serving as a clearinghouse for best practices, tools, techniques, algorithms that are relevant. But I think of all the disciplines in science that could be a front runner in this fusion between computational science and data science, I think it's astronomy. And if I think of anywhere in the country to make that play, it's here in California because of the 10 campuses and the 3 national labs. Well, 4, including, yes? Well, Los Alamos is included. Los Alamos is included, I think, yes. So it's actually 4, right? Okay, what are others doing? Well, my center, the San Diego Supercomputer Center, is establishing an Institute for Data Science and Engineering. It's a brand new initiative. We call it IDSE. It consists of a collection of short courses focusing on big data systems, algorithms, tools, and applications. LBNL, quite aside from BIDS, has very impressive and aggressive plans in data science. I see NERSC as wanting to complement the leadership computing facilities at Oak Ridge and Argonne by being the leadership facility in data science, and I think that's the right choice. Livermore, Lawrence Livermore National Laboratory. Was there ever a more hardcore HPC shop than Livermore? I just reviewed them a month ago. I was on their external review committee, reviewed the comp division, which is 900 people, and guess what? Oh, this is now out of order, so I'm going to show you some slides on what we're doing. So here's a few slides from Donna Crawford, who is the Associate Director for Comp at Livermore. Basic message is they are embracing data science. So here is the way Donna presented their focus areas. Computation has leadership capabilities in frontier research in 3 areas of excellence: high-performance computing, what they've always been known for; computational mathematics. This is this institute within a lab called CASC that does a lot of really high-quality numerical algorithms and software development. Work is very analogous to what goes on here at Berkeley Lab. But data science is the new thrust. And it's described this way. Data science is the development of new models and tools for data-driven discrete event simulations, new architectures for data-intensive computing, and pattern discovery through machine learning and graph analytics. Here's the nice graphic that you see at reviews like this. And you see this interwovenness between high-performance computing, computational mathematics, and data science. And what was very interesting to me is the computational mathematics division, which previously had been almost 100% focused on simulation science, was now applying many of the same methods to discrete event simulation and graph analytics and UQ and SA, things that are really coming from the data side of things. So this tells me that this is the future, and the future is now. And so I think HiPACC would be very wise to build on the abundant resources, both intellectually and in terms of computing resources, to go that way as well. And so I skipped over, I got out of order here. I wanted to say a few things about what we're doing at, I hesitate to say UCSD, because in this case, SDSC is impatient. Things on campuses move at the speed of funerals. And so, like they said, physics advances one funeral at a time. I forget who said that, but I think it was But, okay, there you go. Yeah. But UCSD is talking about doing something. SDSC, because we're semi-autonomous, we can just do something with our own resources. So this is what we're doing. We're standing up this IDSI, and initially we're just focusing on education through short courses because people are busy and they have other jobs. So the idea is to provide broad access to data science and engineering curriculum, providing practical skills through hands-on exercises, flexible formats, short focused modules, either at UCSD or at your location, customizable content, and we're very connected into the big data industry. Big data is mostly about commerce, and it's about turning clicks into cash. And you have, if you look at the big data industry, you have the vendors on the one side, and you've got the consumers of that technology on the other side. So you've got the IBMs, the Teradatas, the SAPs, and the companies like that. And then you've got consumers like Target, right? They should have done a little better job with their security. But that is what's really driving big data, is that industry. But here's the insight that I got. Just like the Cold War drove the development of supercomputing, which we as academic researchers benefited from in terms of architectures and technology, in the same way the big data commercial push is what's going to define the architectures that we scientists use in the future. And you might think, well, this is actually crazy. This is not going to happen. In my talk tomorrow on big data, I will show you that, in fact, it is happening. I will show you a few slides of data-centric architectures that Livermore is deploying, and they are very much building in commodity parts from the, that are on the drawing board today that will come from this whole big data commercial push, but it's also dictated by that DOE Exascale plan by Congress. So, in fact, there is this alignment and a synergy between commerce, our computer industry, our national labs, cybersecurity, and we're all just going to ride on this wave. No one's going to put $1 billion into computational astrophysics, but they will put $1 billion into an exascale platform, hopefully more than one, that we can all use. So I'll just stop there, and this is my conclusion slide. There it is. I think I've already said it. Yeah. So HiPACC should leverage and contribute to the burgeoning efforts in data science and engineering at Berkeley, UC Berkeley, the labs. I don't know much about what's going on at Los Alamos. I'm not on their review committee, but I imagine it's the same story. NASA Ames has tremendous expertise in data archiving and data access, data management, and they're going in that direction. SDSC and other UC campuses, I think, are going to get on this data science bandwagon. So I think HiPACC could become an organizing principle for a lot of that activity in the next incarnation. And I think it's relevant not just to research, but also education. I think education might be, in fact, the killer app. So I'll stop here. Take questions. Yeah, I totally agree. And I do think that, if I could use the word convergence, I see a convergence between simulation science and observational science, data science, happening in astronomy, if not first, at least sort of coincidentally with maybe genomic science. I mean, that's very data rich. There's not much in the way of sort of simulation base for that. It's mostly data. But I think astronomy has always been at the vanguard of using computers to do its science. And what I find so interesting is how even the effort is now. It used to be observational astronomy, and when I started, there were 5 other computational astronomers in the world, that did simulations, and I knew them all. And now, look, there's more than that in this room. So it's really gotten quite balanced, but also the science is codependent, right? And we see this in the cosmology, that the cosmology requires these enormous simulations in order for the observations to make any sense. So I think astronomy is still very special in terms of the evolution of science methodology.